Okay, this is the last thing of this chapter. I have good news and I have bad news for you. Good news is this is the last thing. The bad news is that limits are back. So today we are going to learn about something called L'Hopital's rule. L'Hopital was a guy, but it's also the French word for hospital, which will come up later. It's not pronounced Le Hopital, it's pronounced as L'Hopital. And this is a guy who invented a rule about limits that requires you to know derivatives. So the reason we didn't learn this rule before is we didn't know derivatives yet when we first learned about limits, but now we do. If we think back, here's what we already learned about limits. You have to stretch way back to chapter 2. When you are evaluating a limit, the number one rule is try to plug in the number. If it works, then do it. If you try to plug it in and it doesn't work, try to use algebra to fix it. You can try factoring. You can try common denominators. You can try multiplying by a conjugate. All of these algebra things can sometimes fix a limit problem so that it is solvable, whereas it wasn't before. Sometimes, however, that's not an option. Sometimes limits approach positive or negative infinity. If your bottom of your fraction is very small, then your answer is very big. So if you try to plug in a number, like the limit as x approaches 3 from the left of 1 over x minus 3, algebra isn't going to help you here because you're just going to get 1 over a very small number, which in this problem happens to be negative because you're a little bit less than 3. It's negative. So you would get negative infinity. Think about this as being like a vertical asymptote. In this equation, the vertical asymptote would occur at the number 3. And when there's an asymptote, you can't cross through it. So you're either going to go up or you're going to go down really, really far in order to try to get around it. Sometimes the x value approaches positive or negative infinity. And when that happens, we need to think about horizontal asymptotes. All we do is we look at the biggest powers on the top and the bottom of the fraction. We reduce that and we try to plug in infinity and see what happens. This is what we already know. However, there are still some problems that we can't solve. For example, this guy right here. You can't plug in 0 because there would be a 0 in the denominator. You can't algebra. There's no factoring, there's no conjugating, there's no making a common denominator. You're not going to get an asymptote there, and you're not going to go to positive or negative infinity. X is approaching 0. So there are still problems where even though we already learned a lot of things about limits, we still can't solve them. Here's the new strategy. If you try plugging your number in and you get either 0 over 0 or infinity over infinity, these are what are called indeterminate forms. Then you can take the derivative of the top, take the derivative of the bottom, do it separately, don't use quotient rule, and then try to take the limit again. And you are allowed to repeat this until the limit works. This is what's called L'Hopital's rule. So let me show you. If I try plugging in 0, the sign of 0 is 0, and 0 on the bottom is 0. This is my indeterminate form. We usually put it in parentheses somewhere to note that this actually happened before we can use the actual rule. So the rule says take the derivative of the top, and the derivative of sine would be cosine. Take the derivative of the bottom, the derivative of x would be 1, and try taking the limit again. This time when we plug in 0, cosine of 0 would be 1 over 1, which is 1, and that's your answer. In other words, all of this stuff that we learned before, a lot of times this will fix those problems without really needing to do the other process. Let's look at some examples. For number 1, well, a couple things. So we call this L'Hopital's rule because that's the guy who invented it. But I like to joke that it's you're sending the limit to the hospital, because his name was L'Hopital, which is French for hospital. You're sending him to the hospital to get fixed. You take his derivative, and now the limit is fixed, and you can try it again. So if I try to find these limits, the first thing is when I'm grading your work, I need to see which indeterminate form you have identified. So in this problem, if I tried plugging in 0, sine of 0 would be 0, and 0, when you plug in 0, is just 0. I like to write that below the limit. Now next to this limit, I'm going to take the derivative of the top. This is the same problem we just did. I just want to make sure you really get it. And we get cosine. And I want to take the derivative of the bottom, and we get 1. And keep in mind here, I'm not using quotient rule. I'm not doing anything crazy. And then I try plugging it in again. If I try plugging in 0 this time, I get 1 over 1, which is just 1, and that's my answer. One tricky thing about L'Hopital's rule, and the reason that I make you write this down, and yes, this is something I'm going to grade, and yes, this is something you have to do, even if you say, I'm doing it in my head, I need to see that. The reason is because if you try to use L'Hopital's rule, but the original problem was not an indeterminate form, it was not 0 over 0 or infinity over infinity, you will actually get the wrong answer by using L'Hopital's rule. So don't go to the hospital unless you really are sick. If you aren't sick and you go to the hospital, bad things happen. So for number 2, let's try plugging in our number. If I plug in the number on the top, the square root of 1 would be 1, minus 1 is 0, and I have 0 on the bottom. It's definitely indeterminate. So I'm going to take the derivative. I like to think about this as being 1 plus x to the 1/2 power. So the derivative would be 1/2 times 1 plus x to the negative 1/2 power. I would do chain rule, but the derivative of 1 is 0 and the derivative of x is 1. So there really isn't a chain rule to do here. And the derivative of this minus 1 from the original is just 0. So this is my final answer. The derivative of the bottom, the derivative of x, is 1. Now all I'm going to do is I'm going to rewrite this in a slightly nicer way. I know that a negative exponent really means I can put that on the bottom, and there's already a 2 on the bottom. Now I'm not worrying about this 1 because dividing by 1 doesn't change anything. Now when I try to plug in 0, I get 1 over 1 plus 0 is 1. 2 times the square root of 1 would be 2, and that's my answer. If you think way back to what we did at the beginning of the year, we would have done this thing by multiplying by a conjugate, looking for something to cancel. It would have been a lot harder. Because of L'Hopital's rule, I just take the derivative and I'm good. Number 3, if I try plugging in pi over 2, secant is 1 over cosine. Now the cosine of pi over 2 would be 0. And 1 over 0 is going to be infinity. So I'm going to get infinity over 1 plus the tangent of pi over 2. Tangent of pi over 2, tangent has an asymptote there. It's undefined there. It's infinity. And I would get infinity again. Infinity over infinity is another indeterminate form. So to figure this out, I would just do the derivative of the top, which would be secant tangent, And the derivative of the bottom, the derivative of 1 is 0. The derivative of tangent is secant squared. One of the secants cancels. So my new function is the limit as x approaches pi over 2 of tangent over secant. Now once again, if you try plugging in pi over 2, you're going to get the same answers that you got over here. So this is one of those cases where you can do this process again in order to try to get the derivative. Before I do that, I'm going to see if maybe trig rules can help me simplify here. Tangent is really sine over cosine. Secant is really 1 over cosine. So the cosines cancel, which means my new problem becomes the limit as x approaches pi over 2 of just sine. Well, now wait a second, that's not indeterminate. Sine of pi over 2 is just 1, so I'm done. Okay. Last but not least, number 4. If I try plugging in infinity, e to the infinity is infinity. 2 times infinity squared is infinity. This is definitely indeterminate. If I take the derivative of e to the 2x would be e to the 2x times 2. The derivative of 2x squared would be 4x. Now when I try plugging in infinity again, I still get infinity over infinity. Before I take the derivative again, I'm just going to rewrite this. So I haven't taken the derivative yet. I'm just putting the 2 at the beginning like a coefficient. All right, now if I take the derivative again, I get 2e to the 2x times 2 all over 4. Now if I plug in infinity, e to the infinity is infinity, times 2 divided by 4 is still going to be infinity, so my answer is infinity. That, my friends, is L'Hopital's rule. It's the way that derivatives are another tool for helping us calculate the value of a limit.